Looking now at exercise 5.1, transformations, it's rendering the same thing, except now it's being transformed. It's being rotated around its z-axis and then translated away from the origin. So the first thing that's different here is in our vertex shader, we are now going to have a uniform, which is a mat4. It's a 4x4 matrix representing a transform, and we're going to apply that transform onto our position vector by multiplication. And that is what we are setting to the GL position. In C++, we're going to bring in a new dependency, GLM, which is the OpenGL mathematics library. It's not officially part of OpenGL, but it's used in conjunction with OpenGL. And GLM is going to bring in for us some vector and matrix types so that we can work with vectors and matrices in a convenient form. With this new dependency, we're going to create a transform value of 4x4 matrix, and that is what's going to be set for the value of our uniform. And note here, it's uniform matrix 4VF. That's what allows us to set a 4x4 matrix as the value of the uniform. Now, to set up the transform, we're combining two prior transforms, translation and rotation. So translation we're creating first with a call to translate, and in the call we specify a vector of 3 floats, denoting translations for the x, y, and z axes. But the first arg is another 4x4 matrix, and what the call to translate returns is this matrix multiplied with the translation matrix that is set up as defined by this vector. And this is really quite strange to me because it has then the effect of creating a new translation matrix and then applying onto it another transform matrix. In this case, calling mat4 with just a single float value of 1, that sets up an identity matrix because we don't want the translation matrix defined by this vector to be transformed. We just want it as is. So when the multiplication is done, it's the identity matrix times this new translation matrix, and that's what we get back. For the rotate function, it's a similar deal. You pass in a vector of 3 floats, which represents an axis of rotation. The second argument is the angle of rotation around that axis. I assume expressed in radians rather than degrees, but I'd have to check. And the first arg is another 4x4 matrix, just like with translate. And so what gets returned from rotate is not necessarily the rotation matrix defined by these two parameters, but that rotation matrix multiplied with transform. And again, in this case, we don't want it modified, we want it as is, so we're passing in an identity matrix for the first argument. So with our translation and rotation matrix, we want to combine them, and because we want the rotation performed first and then the translation, it's translation times rotation in that order. If you flip the order here, it would apply the translation and then the rotation, and you'd get a different end result. Now, because we just want to see the rectangle spin, the angle is just the time. And of course, because time advances at an even rate, then this number gets bigger and bigger at a steady rate. And so this will make the rectangle rotate at a steady rate. So this is how we can set up the transform matrix. But if I comment this out, uncomment here, if instead we create our translation matrix, and that is what we pass as the first argument to rotate, then what rotate will call will effectively be this first matrix multiplied by the rotation matrix, and that then will be what transform is assigned when we get down here. Same result as we had up here. Notice that effectively we're combining our transforms in reverse order. The one that we're defining here first at the top, translate, that is the one that's applied last. So it's in backwards order. And I still do find it strange that they do the multiplication this way. I would expect it to be the other way, but nope, this is how it works. Now, if we look at 6.1 coordinate systems, we are finally doing a 3D projection. Our rectangle here has been rotated on the x-axis, and also the camera has been moved back a little bit. So now in a vertex shader, we're going to have 3 separate 4x4 matrix uniforms. One for the model transform, one for the view transform, and one for the projection transform. We multiply projection times view times model times the position. And again, remember that means that effectively the model transform is applied first to the vector, then the view transform, and lastly the projection transform. Now it may occur to you that we can combine these matrices together all in one go before starting our shader. If they're not going to change from one vertex to the next, it's wasted work to compute the same thing over and over again for each vertex. Down the line, when things get more complicated and we start accounting for lighting, it's going to be the case that for each vertex we want to compute not just the clip space coordinate, but also its view space coordinate. And so we're going to keep the projection matrix separate from the view and model matrix so that we can separately multiply a combination of view and model to get the view space coordinate and then apply the projection transform on that to get the GL position, the clip space coordinate. So in practice, it is common to combine view and model together and feed that into the shader, but we're generally going to keep the projection separate. In this case, for just simplicity and demonstration, we're keeping them separate. And so we're feeding in 3 separate Mat4 uniforms to the vertex shader. So to set up these uniforms on the C++ side, we're creating a model transform, a view transform, and a projection transform, and then we're setting each one to the respective uniforms. What's being demonstrated here is 3 different ways to do so. In the first case, when we call uniform matrix 4VF, we're using this value pointer function from the GLM library and using that to get a pointer to our model matrix. Alternatively, in the second example here, we're simply just getting a pointer to the first byte of the matrix. The matrix has a subscript operator defined such that you can access its columns and rows with the subscript operator. And then for the third case, the shader class that's been defined has a convenience method set mat4 for setting a mat4 uniform, in this case, with the name projection and the value of the projection matrix. So what about these matrices? Well, for the model matrix, what we're doing is we just want to rotate it a little bit on the x-axis. So here, the rotate function, we're specifying a vec3 of the x-axis. The angle is -55 radians. And again, we're just plugging in an identity matrix because we don't want this rotation modified. We just want it verbatim. For the view matrix, we want the camera to move backwards. Otherwise, we're not going to see anything because if you recall, our rectangle is starting on the XY plane. So we need to move back to see it. So to move the camera backwards, you would add to the Z value. But of course, we're not actually moving the camera. There is no camera to move. We're instead moving everything in the world in the inverse way. So in the view transform, we're going to move everything down the negative z-axis. We're going to add -3. Now, where things get complicated, at least if you want to fully understand it, is setting up a projection matrix. We're calling here perspective, which will return a perspective matrix, which is defined such the horizontal field of view, what the so-called FOVY, F-O-V-Y, is 45-degree radians. It has an aspect ratio for its view plane, which is equivalent to the aspect ratio of our output resolution, 800 by 600. The near clipping plane is defined at 0.1, and the far clipping plane is defined at 100. And with this information, the perspective function can return a projection matrix. And this may be confusing because it's different from how I explained projection. I explained projection in terms of a defined focal length and a width and height of the viewport. But here we're not plugging those values in. Instead, we're plugging in an angle for the field of view, the horizontal field of view, FOVY, FOV, and an aspect ratio for the view plane. What's happening is from those 2 pieces of information, the perspective function can compute a focal length and a width and height for the view plane. Looking at this illustration, you can see that the rectangular cone of vision is diagrammed as a 4-sided pyramid. And you see also where our near plane is defined and the far plane, creating our frustum. And the angle in this pyramid between the top side and the bottom side, that is the FOVY, the horizontal field of view. And though we haven't defined any focal length, consider that for this cone of vision defined by the field of view, the view plane can go anywhere in the pyramid. Any rectangle bounded by the pyramid that's parallel to the XY plane would be a valid view plane. And so in the diagram, they are designating effectively the near clipping plane to also be the view plane. But understand it would be the same projection if instead our view plane were defined to be the far clipping plane instead. For a given projection, there's not just one possible combination of view plane width and height and focal length. As the focal length increases, the width and height scale up. And as the focal length decreases, width and height would effectively scale down. We have effectively a whole continuum of options. What's usually done, however, is we just simply select the near clipping plane to be our view plane. And so then for our projection matrix, we can compute what the focal length is. It's simply equal to the length of the near clipping plane. And then with the little trig, we can compute half the height of the view plane and half its width. because the z-axis through the view plane forms a right triangle with the top of the pyramid, we get the tangent of half the fovi and multiply that by the focal length, which again is equal to n, the distance to the near clipping plane. And that gets us half our height. Because we also know what the aspect ratio between the width and the height is, once we have half the height, we can then multiply it by that ratio, that aspect ratio, to get half the width. And so now we have all the information to set up our projection matrix, following the formulas I showed you to get from view space to clip space. Because we now actually want to compute our projection matrix, I'll show you exactly how to compute the z of the clipping plane. So the problem again is that we want to scale z values from the range of n to f into the new range of negative n to f. And we can do that first by adjusting the z values to a range that runs from n to f, but oriented on 0. So we subtract n from z. And then for that adjusted z, we want to know proportionally what percentage of the distance from n to f is that. So we divide this value by f minus n, and we have effectively a percentage, which we want to then apply to the full new length that runs from negative n to f, whose distance is equivalent to f plus n. The last step is to subtract n, because before we subtract n, we have a value which is in the range from 0 to f plus n, not negative n to f. So if we subtract n, now it's in the range of negative n to f. Now we have the formula for z of clip space, but the problem is it involves first subtracting from z, then doing a multiplication, and then another subtraction. But for a projection matrix, we're going to need to express this as a single multiplication and addition. We can't have that subtraction between the multiplication. Fortunately, if we go through a few steps, we can work out an equivalent formula, which is z times f plus n divided by f minus n minus 2nf over f minus n. And so now we have a formula we can plug into our projection matrix. So what the projection matrix is going to look like then is x is going to get simply multiplied by n over half the width of the view plane. The y values are going to get multiplied by n over half the height of the view plane. The z values are going to get multiplied by f plus n over f minus n, and then we subtract out 2nf over f minus n. And lastly, the w values is just the z value multiplied by 1, so the z value verbatim. And that's how we get from view space to clip space, by applying this projection matrix. Except again, actually I lied to you in the prior video. The camera in OpenGL is presumed to be facing down the negative z-axis, so all of our z values are in the negative range, not positive. And so going to clip space, first thing is we actually want to flip the sign of our z values and then apply the formula. So effectively that just means we need to flip the sign of f plus n. And then for our w values, because the x, y, z's of clip space are going to be divided by the w to get to NDC, normalized device coordinates, well, we don't want the w values to be negative because then all the signs would flip. We don't want our x, y, and z values to have their signs flipped. So we're taking the z value, flipping its sign, and that is what the projection matrix calculates for w. So now, for the perspective call that was in our code sample, if we actually run the numbers, what we should get is a projection matrix that looks like this. For the x values, it's about 1.8. For the y values, it's about 2.4. For the z values, we multiply them by about -1 and then subtract 0.2. And for the w values, as always, we simply multiply the z by -1. So back in our code here, I'm going to add this line that will print out the value of the projection matrix, and we can verify if this is the case. So I'm going to build the code, run the program, and what do we see? Well, 1.8 checks out so far, 2.412, that's good, that's what we expected. And then -1, -1, wait a minute, if this is the third row, something's off, and then on our fourth row, it's not -1, it's -0.2. So strangely, it looks like these two values are swapped to the -0.2 and the -1. Well, what's simply going on here is that for whatever reason, when it prints out these 4x4 matrices, what we're seeing are the columns, not the rows. So this first group of 4 numbers is the first column, the second group of 4 numbers is the second column, the third group of 4 numbers is the third column, and then this is lastly the fourth column. So it is correct, it is what we expected. It's just printed out in column major order rather than row major order like we expected. Next, we have 6.2 coordinate systems depth, and now we're rendering a full cube. And now that we're rendering things which may get drawn on top of each other, it's very important that we enable depth testing by calling GL enable depth test. If we forget to enable depth testing, this is what we'll get, because what's happening here is the primitives are being rendered in the order they happen to exist in our array of vertices, and so sometimes primitives which should be drawn behind others are being rendered after, and so they're just being drawn on top of things that they should be behind. So don't forget to enable depth testing. Aside from that, there's not really anything new going on here. We just have a bunch more vertices to make up all the sides of our cube. And down when we render, we are rotating on an axis that is not one of the X, Y, or Z axis. It's a rotation axis that is not one of the 3 cardinal axes. That's why the cube seems to tumble in multiple directions. The only other thing that's different here is that when we call draw arrays, we specify that we are drawing 36 vertices, not just 6 like we were before. Here in example 6.3, coordinate systems multiple, we're now rendering the same box but with multiple instances. What's going on in the code here is we've added another array cube positions of vec3s, which are the positions where we're going to place our cubes. And this is not being put in a GL buffer. We're not actually going to store this on the GPU side. Instead, just in our rendering loop, we're taking those cube positions, creating a model transform, and applying a rotation on it, always around this axis, but with different angles as determined by the counter of the loop, I. Setting that model to the uniform, and then calling draw arrays each time in the loop. So whereas before, in each frame, we're just making one draw call, now we're making multiple. This is not ideal, because for various reasons, draw calls are quite expensive. There's significant overhead when you issue a draw call. Generally, we want to keep down the number of draw calls in any one frame. And so in a later example, we'll look at instancing, where with a single draw call, we can render the same model multiple times, but with different model transforms. So the instances are rendered in different places. What we have here, however, is the simpler, more obvious solution. Looking at example 7.1, camera circle, now we have camera movement. And what's happening here is that our camera is moving around the origin point. It's circling around it, orbiting, and looking always at the origin. So each time in the render loop, we're setting a new view matrix, defined here. And we're constructing this view matrix with the convenient lookat function. The lookat function takes 3 points, and the vector from the first point to the second determines what direction we want the camera to look at. So imagine the camera positioned here, but looking towards this direction. And then the third point, this is our up direction. So for the line between these 2 points, the question is, how is the camera rotated on that axis? And that is what this is effectively defining by pointing upwards. In this case, our lookat direction is always going to be flat on the XZ plane, and up is straight up on the y-axis. So our camera perspective is always going to be, in a sense, level with the ground. Now for the orbiting effect, we're changing the position of the camera, and by taking the sine and cosine of the time value multiplied by a radius, we get x and z values that effectively orbit in a circle around the origin, and we're always looking at the origin. Now, I'm not going to go into the math of the lookat function. It's something you could actually probably figure out for yourself when you realize what we're doing is we're positioning the camera at this location, making it point in this direction, and rotating around that origin defined by this up vector. Having established a transform to get a camera into that position, remember that we don't really transform any camera. Instead, we transform everything in the world around the camera with the inverse transform. So once we've computed that camera transform, we get its inverse, and that is our view transform. So that is what lookat is going to return. In example 7.2, camera keyboard DT, DT standing for delta time, we now have keyboard controls of WASDA. I can move forward, back, and strafe left and right. And in this example, we now need some global variables. We have first a variable camera position representing where the camera is positioned, camera front, which is a vector relative from camera position determining which direction the camera is facing, Camera up, which is also relative from camera position, determining which way is our up vector. For the camera's facing direction, which way is up, what is the rotation around that axis. And we also are defining delta time at last frame. Last frame is going to store the timestamp of the previous frame, and delta time is going to store the difference between the timestamp of this frame and the last frame. How much time has elapsed since the last frame. And this is standard game loop stuff where when it comes to movements, we want to regulate speed of movement based on how much time has actually elapsed because of vagaries in the system. You know, the time between frames elapsing is never perfect. Sometimes it takes much longer to get from one frame to the next than normal, than average. So you should always factor in how much time has actually elapsed between frames. That's why we get delta time. That is computed first thing in the render loop, where first we get the current frame timestamp, get delta time by subtracting that from last frame, and then get last frame by setting that to current frame so that next time around we have it stored. And then for our view transform, we're using lookat again. The position of our camera is defined by camera position. The place it's looking to is camera position plus camera front. Again, camera front is defined relative to camera position. So we need to add it to get a point where the camera is looking at. And then the up direction is defined by camera up, which in this example is never going to change. Camera position, though, does need to be affected by our keyboard input, WASDA. So down in process input, first we want to compute how fast the camera is moving based on delta time. So we just have this constant 2.5. If we increase this, we would get faster camera movement. If we decreased it, we would get slower camera movement. And in the case where we hit W to push the camera forward, well, camera front tells us which way the camera should go. And in this example, you may have noticed there's no way to change the direction of camera front. So it's always going to be the same in this example. But we multiply that times camera speed and then add the result to camera position. We're taking two vectors, adding them together. And so if we're moving forward, this is going to mean that the z value is decreasing, because if we move forward in OpenGL chords, then we're going down the negative z-axis. For S, for moving backwards, same deal, except we're subtracting, so the camera position z value should get bigger. And then for A and D, for strafing left and right, we need to get the vector which is the cross product of camera front and camera up, because camera front and camera up form a plane, and the perpendicular vector is computed from the cross product, and that tells us which way to move left, multiply that by camera speed, and subtract it from camera position to go left, add it when we push D to go right. Now in example 7.3, camera mouse zoom, we've added the ability to, in addition to WASDA, to move the camera back and forth and strafe, we can use the mouse to change the forward-looking direction of the camera. Also, we can use the mouse wheel to zoom in and out. So we're changing effectively the field of view. So in the code now, we have a few more global variables, including some variables describing the mouse state, as we'll see when we look at the mouse handling code. And from the mouse state, we're going to update these other global variables affecting the camera state, yaw and pitch, which describe the orientation of the camera, the facing. And so from these, we will update camera front. FOV, the field of view, that's going to be modified by the mouse wheel. And the field of view then simply factors into the view transform when we get our perspective matrix. The field of view is no longer hard-coded, it's from this global variable FOV. Now to handle mouse input, at the top here, we're going to set two callbacks. This first one, set cursor position callback, this callback handles the change of the mouse cursor position, and set scroll callback, that's for the mouse wheel. So looking at this function first, this one's simple. We get two inputs, one for X offset of the wheel and one for Y offset of the wheel. The Y offset is for the up and down scrolling, X offset is for left and right scrolling, because there are some mouse wheels on some mice that do scroll left and right, but most just scroll up and down, so we just care about the Y offset. And in their field of view, we're going to cap the field of view between the range of 1 and 45. It has to be somewhere in that range. So only then do we update the field of view. And so we take the Y offset and subtract it from field of view. I assume Y offset is negative when you scroll down and it's positive when you scroll up. And when we scroll up, we want to zoom in, which means decreasing the field of view. So that's why we're subtracting here. And then having computed a new field of view, we want to make sure it's capped in the range of 1 to 45. So that's what this logic is about. For the mouse movement handling, there's this key callback up here in the setup code where we set input mode to glfw cursor and cursor disabled. This effectively captures the mouse for our window and doesn't display a cursor within it, which is what you want for an FPS. You want to be able to move your mouse around while you have focus in the window, and you don't want to see the cursor poke out of the window, and you definitely don't want to see the cursor within the window either. So the callback for this, it gets an X and Y double value denoting the position of the cursor. And for our purposes, these values only really have meaning relative to prior values. So from one call to the next, what we care about is how the X and Y values have changed. So that's why we have the global last X and last Y values to record what the X and Y positions of the previous call were. But for the first time this is called, we want the X offset and Y offset, the deltas between the X and Ys, we want that to be 0. And so we have this global first mouse, which is starting true, but for the first mouse event, it's going to set X and Y to the positions first thing, and then disable this so this won't run again in any subsequent call. I find this a little strange. I would have just set X offset and Y offset to 0 for the first call. That would have had the same effect. But anyway, this gets us what we need. And so once we have the X offset and the Y offset, we multiply them by a sensitivity factor. The larger the sensitivity value, effectively the larger the mouse movements. And with that offset and Y offset, we add them to the yaw and pitch respectively. For the pitch though, we want to make sure it's capped within a range of 89 to negative 89. Because certainly you don't want to have your perspective sort of do a backflip. So you've exceeded 90 degrees or negative 90 degrees. You don't want to do that. So that's why we're capping the pitch. And from yaw and pitch, we now need to update camera front. We create a front vector where we're computing its X, the Y, and the Z using this trigonometry. I won't go into the details. You can figure out the geometry for yourself if you're curious. And lastly, we normalize the vector because we want our camera vector to always have a length of 1. We want it to always be a unit vector. So by updating camera front, that's going to affect our view matrix in the call to look at. And last thing here, do be clear that the handlers for the mouse events, those are processed when we call pull events. When pull events is called, that's when it reads events off of the event queue for the process, the events coming from the operating system. And when mouse events are pulled off this queue, that's when it calls the mouse handlers.